Hello friends, in continuation with the previous video, there is going to be another problem on shallow foundation and bearing capacity. This is 2023 set 1, and this problem is uh, to calculate the ultimate bearing capacity of the plate by using Tarjagi's theory. The problem is like this: a square footing of 2 meter by 2.5 meter by 2.5 meter and depth of footing is 1 meter is embedded in phi soil. That means it is embedded in cohesionless soil bed. Groundwater table is at footing base, and the unit weight uh, above the groundwater table is 18 kilonewton per cubic meter. Saturated unit weight is given to you as 20 kilonewton per cubic meter, and the bearing capacity factor NQ is given as 58, and the net ultimate bearing capacity of this footing is given as 1706 kilopascal. Unit weight of water can be taken as 10 kilonewton per cubic meter. Earlier, during dry season, a plate load test (PLT) on a circular plate of 0.3 meter dia was performed using Tarjagi's theory. Calculate the ultimate bearing capacity of the plate. So this is in toto the problem. So the best thing is just see first the foundation part. The foundation part is you have a square footing embedded into phi soil and soil bed, and all the details are given to you. The groundwater table is touching the base of this footing, and the net ultimate bearing capacity is given so much of kilopascal. So what is the formula for net ultimate bearing capacity? That you can always calculate the net ultimate bearing capacity because it's a phi soil. So the first part is not going to be in picture. The another part is going to be C is going to be 0 here. So because C equal to 0, C and C part will be 0. The second part is going to be Q into NQ minus 1. So because it is net ultimate, so Q into this NQ minus 1 plus now it is a square footing. So if you use the Tarjagi's bearing capacity equation for a square footing, this will be 0.4 gamma B n gamma into water table correction factor. So this is the formula. So in this expression, you can substitute the first part here. Q will be gamma times dF. So the surcharge here at the base of the footing, this will be gamma times the depth of the footing, and gamma above the base of the footing is given to you as 18. So Q will be gamma, that is 18, into the depth of the footing, and depth of the footing is given as 1 meter. So this is the value of Q. NQ is already given to me as 58. So 58 minus 1, this becomes 57 plus 0.4 for a square footing multiplied by gamma. This gamma is to be taken as gamma saturated. So this is the third term where you take, this is going to be gamma saturated, which is given in this problem as 20 kilonewton per cubic meter, and the width of the footing is given to you as 2.5 meter. That's given over here. And n gamma is not known to you, multiplied by water table correction factor, because it is going to touch the base of the footing. The water table correction factor is going to be 0.5. You know the expression for water table correction factor, that you already know it. So the water table correction factor is going to be 0.5 into 1 plus ZW divided by B. Here ZW is 0 because it is touching the base of the footing. So the depth of water below the base of the footing becomes 0. So this becomes 0.5. And therefore, the W dash equal to 0.5. So now, if you simplify it, you will be able to get the value of n gamma. So we will calculate it and we will get the value of n gamma. So 18 so this becomes 1026 plus this becomes 10 times n gamma, and the Q and U value is 1706. Therefore, n gamma equal to 1706 minus 1026 divided by 10. Right? 1706 minus this divided by 10. That's the value of n gamma. So let's calculate. It is equal to 68. So the bearing capacity factor n gamma equal to 68 that you have calculated. Now the second part of this problem is for the plate. The plate is circular in nature, where you need to calculate using Tarjagi's theory. For the circular plate, you will have to calculate the value of QU. So QU for the circular plate, and plate load test is carried out on the surface. At the foundation level, you are going to put the plate, circular plate of diameter 0.3 meter. So for circular plate, the third term will only come into picture, because this term is going to be 0. There will not be any surcharge, and the value will be 0.3 for the plate. So I can write it P for the plate. So ultimate bearing capacity of the plate will be 0.3 gamma B n gamma, and it's during dry season. So during dry season, there will not be any effect of the water table. So because there is no effect of the water table, it will be W prime will be 1, and therefore we can calculate 0.3 into gamma. So gamma is going to be 18, and the width is going to be width of the plate 0.3 gamma B, that is 0.3 meter, and n gamma we have calculated is 68. So if you calculate 110.16 kilopascal. Therefore, the ultimate bearing capacity of the plate will be by using Tarjagi's theory. So we have been able to calculate the answer. So this is the answer of this particular problem. So you can see how simple it is. You can calculate it. So this becomes the answer. So I hope I am in a position to calculate it and you understand the concept. Now we will go to the next problem, that's of 2022. So friends, now the next problem is like this: 2022, and this is set 2 gate problem. Here, so many options are given to you in this problem. The options are in the form of P, Q, R, S. So P is while designing a shallow footing, designing a shallow footing in sandy soil, monsoon season is considered is considered for critical design in terms of bearing capacity. Whether it is true or false, we can discuss it. You know that during monsoon, there is always going to be water table is going to come up, and sometimes it touches the ground level, and therefore the water table correction factor comes to both the second term of the bearing capacity equation and the third term. So this due to monsoon, the critical design in terms of bearing capacity of any footing, any foundation, it's a critical design because the water table correction factor will come into picture during monsoon. So this is a statement, whether it is true or false, we can say it is true. Then the Q is for slope stability of an earthen dam sudden drawdowns is never critical. condition. So in earthen dam, you know that sudden drawdown, the water level goes down. There's the water is going to come on the upstream side itself. So the flow lines all will come, and it is going to be critical condition because it can lead to failure of your slope. So it is critical for the stability of the slope stability. So this is false. It is called never critical, though it is critical because the flow lines are going to be, the water is going to come on the upstream side, leading to failure of the upstream slope. And therefore, this is a false statement. Then, in a sandy sea beach, in a sandy sea beach, quicksand can arise only if the critical hydraulic gradient exceeds the existing hydraulic gradient. You can examine this statement and you can decide whether it is true or false. So you can easily say that the quicksand is a condition. And you know, the hydraulic gradient depends upon the delta H divided by L. That is, what is the head loss divided by the length. And when this delta H becomes almost equal to 1, the critical hydraulic gradient becomes 1. And it leads to a condition known as quicksand condition. And the upward force and the downward pressure becomes equal. So it has nothing to do with the existing hydraulic gradient. It's a condition. So critical hydraulic gradient is a condition where the value of I critical, the hydraulic gradient I critical, becomes unity. And therefore, it's a false statement. This is a false statement. And the last statement, which is given, and you can examine this, active earth thrust. Active earth thrust on a rigid retaining wall supporting cohesionless or phi backfill. The backfill is cohesionless backfill. Normally sandy backfill are used. Will reduce reduce with lowering of water table, with lowering of water table uh, in the backfill. In the backfill. So if you have a rigid retaining wall and you have a backfill, this backfill is mostly sandy, that is phi soil, cohesionless material. Now, when the groundwater table is touching the top of the backfill, then the active earth pressure, you can draw it. The active earth pressure is going to be a triangular variation, and it is going to be K. Now, because it is underwater, so this is K into gamma prime into H, where H is the height of the wall. At any depth Z, this will be K gamma prime Z. So this is the height Z. Now, let's say the water table is going to be lowered. So in a rigid retaining wall, let's say now the water table has gone down. So what will happen now on active earth pressure? You say here now the unit weight is going to be total unit weight, and this is here it is going to be submerged unit weight. So here at this level, this pressure will be K times gamma T into, if the height is H1, it will be H1, and this pressure will be at the base K times gamma T into H1, and then now it is underwater. So from here, this pressure will be K times gamma prime now, because it is now gamma prime into, let's say, this height is H2. So now you see, because of the lowering of water table in the backfill, what's happening to the active earth thrust? Is it reducing or it is increasing? With lowering, the pressure is increasing. So here it will be plus the pressure due to water also. So here it will be Kw is going to be 1. So gamma W into H. And gamma W is going to be this half of the total unit weight, almost 50%. So if you see in the light of this pressure distribution diagram and calculate the active earth thrust on a rigid retaining wall supporting phi backfill, it will not reduce. On the contrary, the thrust will increase. So will reduce is false. This is a false statement. So here P is true, Q is false, R is false, right? So R is also false and is also false. So true, false, false, false is the answer. So this is asked in 2022. A simple analysis you can do it with your knowledge of shallow foundation, and you can uh, examine in the light of geotechnical and foundation engineering knowledge, and then you can decide which is true, which is false. So that is asked in 2022. Now I will go to 2021. My intention is to cover all the problems on shallow foundations one by one, but I will expedite slowly so that you understand it conceptually. Now, I will go to the next. This is gate 2021 set 2, and it's on rectangular footing or rectangular footing uh, of size 2.8 meter by 3.5 meter. That means B is 2.8 and L is going to be 3.5 meter, embedded in clay. So it is embedded in clay bed, and the eccentricity in x direction is 0.8 meter as shown in figure. Figure is given in the problem. So if you see the gate paper, there is the ground level and you have a rectangular footing. There is the rectangular footing where B equal to 2.8 meter. This is the x direction, and the eccentricity, this is the center line of the footing, and the eccentricity is given to you. So load is acting here over the footing, and this is the eccentricity Ex, which is given to you in this problem as 2.8 meter, and the depth of the footing is given as 1.5 meter. So this is the depth of the footing. And the properties of the clay is given to you. The properties of the clay, what are the properties? You need gamma. So the value of gamma is given to you as 18.2 kilonewton per cubic meter, and C equal to, or Cu equal to 40 kilopascal, and phi 0 degree. So these informations are given. Also, you are given the bedding capacity factor NC, because it is clay soil. It is given as 5.14, and you are given as NQ equal to 1. If you see Madoff table also, you will be getting these values, but it is given in the problem, and N gamma equal to 0. So supplied. The shape factor is also given to you. S equal to 1.16. That is also given. And SQ and S gamma, the shape factor, are given to you as unity. DC, the depth factor, is given to you as 1.1, and DQ, D gamma are given to be 1, and the inclination factor I is also 1 because the load is acting vertically in the downward direction. Naturally, it has to be 1. Only when the load is inclined, based on the alpha value, the code says how can you calculate the inclination factor, because the load is acting in the vertical jet direction, and therefore it has to be 1, and it is given that inclination factor is 1. Calculate the load that can be applied. Calculate the load that can be applied with factor of safety equal to 2.5 using Meyerhoff's theory. So, simple problem. Now again, there's all informations are given. If you know the Meyerhoff equation, you can find out the load that can be applied to this footing. First of all, let us see the solution of this problem. Now, there is an eccentricity in the x direction, therefore, the corrected width will be b minus 2 times ex. So, ex is already given as in this problem as 0.8 meter, and therefore it becomes 1.6. So 1.6, 2.8 minus 1.6, 1.2 meter. So you know the value of b prime. Now, in order to calculate the load, let's calculate the net safe bedding capacity. I will tell you the shortest way of calculating it. It will be 1 upon the factor of safety into Q net ultimate. So Q net ultimate divided by factor of safety will give you the net safe. So how will you calculate this? It will be 1 upon F, factor of safety, and for this soil, the net ultimate will be CNC into shape factor, depth factor, inclination factor plus QNQ, QNQ minus 1. Now you see what is the value of NQ? Bedding capacity factors are given to you. It is 1. So 1 minus 1 becomes 0. So this terms become 0. And what is the value of N gamma? 0. So the last term will also become 0. 0.5 gamma B N gamma. So N gamma is 0. So last term is going to be 0. Need not be written. The second term also becomes 0. Need not be written. So finally what you are landed with is 1 upon F, the net safe bedding capacity is simply C. C value is given to me in this problem. It is 40. So 40. NC value is given to me as 5.14. Shape factor is given to me as 1.16. Depth factor DC is 1.1. Inclination factor is 1. So in kilopascal, I can calculate it. And once I calculate this, then I can apply the net safe load that this footing can carry, which will be equal to the net safe bearing capacity into A prime. A prime is the corrected area, and the corrected area is going to be quite simple. B prime into L, and B prime is already known to me as 1.2 meter, and 3 L is 3.5 meter. So I can calculate this in a square meter. So I know this, I can calculate this. This I am going to calculate. So let us take our calculator, calculate it, and that becomes the answer. So Q&S, this becomes the my answer. So you see, in one step itself, you can find out the solution. There is nothing that you should go for ultimate and then net safe, nothing like that. Net ultimate divided by factor of safety. So if I calculate it, the calculation becomes quite simpler. Factor of safety is given to me as 2.5. So here, factor of safety is 2.5. So this becomes 2.5. So 40. 40 into 5.14. I am getting 104.93 kilopascal, and the area I am getting 1.2 multiplied by 3.5, 4.2 square meter. So QNS will be 104.93 multiplied by the area. Corrected area is 4.2 kilonewton. So if I calculate it into 4.2 into 104.93. So the answer is 440.706 kilonewton. So friends, you can see that all of you can do it very quickly in the examination. This becomes the answer. This is the net safe load that this footing can be applied. So that was the question, the load that can be applied with factor of safety to use. And you have to use Mehrhouse theory. So in one step, you can find out the solution. Now we will go to the next problem. The next problem is this 2021, and now 2021 set 1. So let us see the next problem. You can give your comments regarding the steps being followed, so that if you need any further clarifications or any help, I will be able to give you these few tips that will help you in the examination. Now, the next problem is calculate maximum depth. Calculate maximum depth of unsupported excavation of unsupported excavation in the soil having C equal to 15 kilopascal. So quite soft. The value of C is given to you as 15, and phi, the angle of internal friction, is given as 20 degree. And the unit weight gamma T is 17.5 kilonewton per cubic meter. So maximum depth of unsupported excavation. So you are going to excavate this ground. So if you are going to excavate, what is the maximum depth? Let's say the maximum depth is H. The properties are before you. Now, when you are removing the soil, the overburden pressure you are going to remove, and the lateral pressure will come into picture. So if you take any element of the soil, any element, it is acted upon by the vertical pressure, and also there is going to be horizontal pressure in the lateral direction. So the vertical pressure is always more than the horizontal pressure. You can say it is the Mayer-Judd principal stress. This is called the minor. So I am talking about the solution part. How to find out the value of H? Naturally, the relation between sigma 1 and sigma 3, you know, sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha in cohesive soil. Now, it is the vertical pressure, this is the horizontal pressure, tan square alpha plus 2c tan alpha. So, the horizontal pressure is the active pressure because it is going to be in tension, right? So, now if you want to find out this, the active earth pressure which is acting is going to be sigma v, you divide it by tan square alpha, that means it becomes cot square alpha minus 2c cot alpha. Now cot square alpha is called coefficient of earth pressure, which is equal to 1 minus sin phi divided by 1 plus sin phi, and the value of alpha is 45 plus phi by 2. All of you know this basic concept. So I can write it, this is going to be gamma z, vertical pressure at any point z. This will be gamma into z. So you can say gamma z k minus 2c under root k. So when there is going to be negative pressure, so at the top when z equal to 0, it is going to be negative pressure. So how the pressures are going to change? It is going to be negative at the top and then it becomes 0. So where it is going to be negative, at z equal to 0, this term becomes 0. It becomes minus 2c under 2k, where at z equal to 0. And PA will be 0 at certain depth, let's say at z0, z0. So at z0, it becomes 0. So what is the value of z0? You can find it out. Therefore, gamma z0 into K equal to 2C under root K. Therefore, Z naught equal to 2C under root K divided by gamma into K. So finally it becomes 2C divided by gamma under root K. Now this is negative. So this Z naught up to here and Z naught on the positive side will nullify each other. So that becomes the critical height. So total critical height H. So therefore the critical height H becomes 2 times Z naught. So the formula for the unsupported excavation in the soil will be 4 times cohesion divided by gamma under root K. So this is the concept, and concept is more important. So this formula you should use it. Now 4 into 15 divided by 17.5 into K value you can easily calculate. So K becomes 1 minus sine 20 divided by 1 plus sine 20. If you calculate this part, you can easily get it. So press your calculator and get the value. So I will be also doing this. So my answer, I can tell you. Sine. It is 0.49. So I get this value as 0.49. So here I will substitute. And if you calculate this, so root of, I will calculate. Simple calculation, 60 divided 60 divided by 17.5 multiplied by under root 0.49 bracket closed. .897. So the critical height H equal to 4.89 meter. So calculate the maximum depth of unsupported excavation in the soil will be H equal to 4.89 meter, and this is the answer of this problem. So friends, I hope with this I have completed up to 2021. In my next video, I will be taking up the remaining problem, and my intention is to cover all types of problem on silo foundation and bearing capacity. So I hope you have got better exposure in this video. Thank you very much.